Good afternoon, all. I hope you're all doing well. Vipul sir, good afternoon.
Yeah, good afternoon. Good afternoon to all.
You can start the session, sir.
Okay. So, yeah, yesterday we were discussing about algorithms. So, there was a factoring algorithm. They have reduced to that. And then we have seen some Qiskits coding, which was running on that. So, today also we will see some continuing that coding also. Before that, I will introduce some of the hardware point of views. Okay, and so let me share the PPT. Hmm. Yes, wait a minute. Hmm. So, okay, straight to begin. So, today we will see some hardware insights. So, what are the developments of the inside the hardware? So, what happens actually in the first day, we have discussed about why we are moving towards the classical to quantum computation, and there are some of the reasons why we are going on the quantum because of the restriction of our ICs, right? So they are going down in the size, and the limit is only and only 1 nanometer. So when this limit will be reached, then there will be a uh, no development beyond that limit of the ICs. So we have to go on the development side. We have to go on that highway also, but we have to keep in mind that uh, there is a limit also for the this hardwares. So, what is the limit of that hardwares? Because we have to understand the basic thing between classical backbone and quantum backbone. So basically, in some sorts we have discussed in the first day that basically in the classical there is a quantity of parameter called current. So from that current we are controlling each and everything, right? But at here in the quantum, the quantity is more towards the atomic level. Actually, there are three levels. You can broadly classify. So there is macroscopic level, one is microscopic level, another is nanoscopic level, right? So in the macroscopic level, these are the quantities that current, voltages, resistances, all the quantities are counted at the macroscopic level, because we are able to measure all these things by measuring the by applying the daily life or daily routine instruments. So we need not to be so much precise. We need not to be so much accurate in that. No special instrument are needed. But when we are going on the microscopic size, so in the microscopic and nanoscale size, there are further more instruments are needed, which is needs to be more precise and which is needs to be more accurate. Okay, the accuracy mean to say here, the accuracy doesn't mean that suppose I am saying that in macroscopic level the accuracy is not needed. Accuracy needed, but the more precise accuracy is not needed. So suppose in the macroscopic we are measuring 1000, then in the 1000 there is a 0.1 of mistake that can run. But when when we are going in the micro and nanoscopic level, then the same accuracy, that is 0.1, and we are measuring a 1, then this 0.1 percentage is something different in 1, and this some different percentage is something different in 1000. So that means to say accuracy. So uh, accuracy is needed more precisely in the microscope, right? So with that detail, there I will begin with the current, and I will begin the classical quantum. What happens in the classical? In the classical, we are dealing with the on and off state. We have to deal with the on and off state only. In the atomic, we have to deal with the on, off, and superposition of on and off, all that states. And principally, we are saying that we were discussing that this superposition states may be of thousand or infinity states. Yeah, there is no limit of that superpositions. Okay, because we have discussed that 1%, we have discussed about these pairs: 1% 99, 2% 98, 3% 97. So these are not the pairs. So these are the superposition states, and only these are not the pairs. In between, in between that, there will be a pairs also, 1.1 and 98.9, like that. This is also called pairs. Okay, so that's why theoretically superposition states there is no limit. Okay, but we are saying in the in our wordings. Okay, but how to realize these things in reality? That is named hardware. So classically, what we are realizing in the classical 1 and 0 bit, what we are realizing? We are realizing by the help of the current. If the current is present, we are calling it a on or 1. If the current is absent, we are calling it a off. But because we need only on and off, and that we are running with the currents only. So we can have only the one parameter, that is current, in the classical, right? So we are realizing this 0 and 1 in the form of presence or not presence of current. So that means you can say we have coded the presence of current as a 1, non-presence of current as a 0. And this is also not the way. This is only not the way. We can also suppose like that. Suppose somewhere the current is 0.5 ampere, and at somewhere current is 3 ampere. So it depends on us that we can code this off. We can code this off to the low current. That is a small current. We can code it. And we can code it this 3 ampere. Whenever the 3 ampere will come, it will be understood by 1 as a 1. Okay. So these things we can choose it very easily. Okay. So overall we are running on the current of microscopic level, and for that realization of current, we are having a lot of devices, because everybody has read in the 11th 12th that we have the diodes to realize, we have the transistors to realize flow of current, and in the transistor also we have input of currents: base current, collector current, and emitter currents, like that. Need not to be worried about that. I know all of you are most of you are from CS background, so need not to be worried about that. Yeah, only I'm telling this hardware side. Okay, so by changing the base current, we are able to control the collector and emitter currents. This is the beauty of the transistors. And by changing the reverse and forward wise, we are able to control the current. Why we are I had to say it here. Why? Because that controlling parameter we want in the hardware side, right? So the controlling parameter is a current here. So when we are applying a positive and negative, like forward wise and negative positive reverse wise, we are able to control the flow of current. At here also transistor, in the base current we are controlling, we can control the collector and emitter current, so that we can control the 1 and 0, and we can code or encode the 1 and zeros, like that. So what happens in the algorithm? When we are designing algorithm, when we are desiring the algorithm, Then that algorithm is going into the machine language, assembly languages. That assembly language is converted into the instructions of coding 1110 like that, binary coding. And because of that coding, this goes to the hardware side. And hardware understand this one means we have to on the transistor. This one means on the transistor. This one means off the transistor. Like that. The transistors are in toggle state always. So we can toggle the transistors. So hardware can decide this one. Okay. So that is the classical one. Now, now coming on to the quantum side. Coming on to the quantum side, what happens in the quantum? We have to deal with the microscopic and nanoscopic level. Okay. When we are dealing with the microscopic level or nanoscopic level, means we are dealing with the less than a 1 nanometer, around of 1 nanometer size. And when we are dealing around 1 nanometer size, so I can tell you the the radius of an atom is of 1 angstrom. That is of 3 nanometer, like that. So that means inside this, because the radius of an atom is of around 1 angstrom, around 3 nanometer. So that means we have to deal with the dimensions which is less than the atomic, right? So this is the challenge. So how we can play and how we can manipulate the atomic level things. Atomic level things means we have to go inside the atom, and we know we can the play of atom how much dangerous. There are atomic bombs, molecular bombs like that. So hydrogen bombs like that. So playing in the atom is a very much dangerous thing. Okay. So we need and there is two point of view. The one is dimension. Other one is energy level. Why I'm talking about all these things? Because all these are the constraint in developing the hardware. And this is the major constant because we are not able to develop the hardware. And this is the major constant we are not realizing the quantum computation algorithm in realities or in practical things. Because until unless we are able to produce such type of mass level production that every so it will be in every cities or it will be in every country, then we cannot progress in the quantum computation. And that is the reason why the National Quantum Mission has been launched here. Okay. So what are the construction constants? There is a dimension and there is energy. The dimension is so much low. We have to be so much precise. It means what it leads, that dimension is so much low. So we have to be so much precise. Okay. So much precise. And the energy, because dimension is so much low, we have to be so much precise, but the energy is so much high. As we are moving towards the atomic level, the energy is so much high. We have to control that energy also. Okay, because we are playing with it. Okay, so this energy is very high. We have to interact with this energy, and there are chances that this energy may interfere whatever we are designing qubits or superposition states. Okay, okay. So, well, this we will deal later. How this energy is interfering with the dimensions and with the qubits. So, yeah. Mm, yeah. So we will deal in this. This is a next section. We will deal with the errors corrections. Quantum errors occurring. We will dealing with it. Okay. Well, we are running here. We are running here in the quantum. We needs there are two constants. The one constant in dimension and another constant in energy. How to play with energy? Okay. So these are the two constants we have to play. So this is means precision. This energy will interfere this precision. Okay. So yes, and now we are coming to the cut to cut quantum. How to realize a qubit? So to realize a qubit, there are various systems. We will talk about that. But in the initial, we will say about that to realize the qubit, we need the three things, very basic three things. Three things is that any parameter or any marker which will understand as 0, or any parameter, any marker which will be understand as a 1. Any parameter beside this, these are the classical bit requirements. So we need that one also there. So we were describing the current 0.3 ampere, 0.5 ampere current we can understand as a 0. 3 ampere current we can understand as a 1. So these are the markers. Okay. So now to whom we will understand 0, to whom we will understand 1. This is hardware engineer understanding. Okay. So this is designer understanding. So any marker, any parameter, we can code it to the 0. Any marker, any parameter, we can code it to the 1 if they are uniformly coming in the circuits. Apart from that, there is one marker also, that is superposition states. Okay. So we have to see that in that system, whatever the system we are going to adopt, there are seven various type of systems. I will not quantify in the numbers because it's R&D. So day by day that number will prove to be wrong. Okay. If I am saying the 7 number of systems like that, then I think there will be 8 or 9. So no more there going on the qubit development side. Okay. So I will not exactly name the numbers systems, but yeah, there are various type of systems so that we can have these markers 0 and 1. We can have this marker also in the quantum superposition. So we have to see in the system that is there any provision. Yes, there will be always a provision marking 0 and 1. Okay, because there will be two markers, energy, low energy state, high energy state. Like that, in the current, we are marking as a low current as a 0, high current as a 1. So the low energy state of the atom, because we know the atom are in the energy state. There is a ground state, there is a first excited energy state, second excited energy state, like that. E0, E1, E2. Okay. So anything we can mark 0, 1. We can mark first excited state as a 0. We can mark second excited state as a 1. Or we can mark ground state as a 0 or first excited state as a 1. Anything we can suppose it as a marker. Now, there is a second thing. This is a challenge, superposition state. So we have to choose that marker. We have to choose that marker in any system, any variety of system, so that there will be always a provision of superposition. That means there is always a condition is coming in the atomic manipulation that there that both the conditions are occurring simultaneously or not. So we have to see this superposition. That is superposition. We have to mark it. So we have to look up for that superposition state also, along with 0 and 1. And why we cannot see these things in the current? Because of the first thing is that current is, yeah, there is always an argument from the student sides. So why we are not seeing in the microscopic quantity like current? In the current, we can always have a 0 and 1, first thing. Second thing is it's a macroscopic property, and we can always have a 0 and 1, but we cannot have a combination of 0 and 1 precisely. Anybody can argue that if we are taking 0.5 ampere, then this is between the 0 and 1. No, this is between the 0 and 1. But this being a between 0 and 1 doesn't always ensuring us that this is a superposition of 0 and 1. We have to take a superposition of these things. Okay. The superposition is a different concept, and taking the value in between, it's a different concept. Okay. So superpositions dealing with the probability of being there or not being there, both probabilities should be there. The provision of being there and not being there. Okay. If we are saying 0.5 ampere current is here, oh, a lot of foolish questions are coming from the student sides. Okay. So if we are taking 0.5 ampere, then it means the current is there. So we cannot suppose a superposition. Okay. So like that. Yeah. So these are the markers we will look up on every system. Okay. So this is the primary line on the hardware side. We have to see any marker for zero. We have to see any marker for one. We have to see any marker for superposition state. Okay. Good. So with this markers, we will move towards our journey of qubits. What are the various systems we will adopt as a qubit? And now we are, how many developments are there in the quantum providers, quantum computer service providers? So, yeah, some of the I have listed here, but it doesn't ensuring that only these type of systems are there only in the market. Okay, whatever I have included here. Okay, but there are so many other systems apart from these things also. I will describe in a little detail that one also. The first very much majority type of systems is superconducting qubits. The superconducting qubits means actually in the physics also, because this is the hardware, so we have to deal with the physics also. So in the physics, there is a condition called superconductors. There are the objects which are called superconductors. Superconductors always appears below than the temperature 200 degrees Celsius. Sorry, minus 200 degrees Celsius. Okay. So below than this temperature, minus 200 to minus 273 degrees Celsius. Okay. At these temperature ranges, anything any conductor, if we are going to on this temperature ranges, any conductor is losing its resistance. Okay, this is another thing that how they are losing resistance. We will not talk about that. Otherwise, it will be a physics class purely. So it loses the resistance. So its resistance becomes a zero at that time. Okay. So when its resistance is a zero, so that means we can have a purely conducting state. That means a one state. We can form it. Okay, so there is a one marker, right? So another marker, we cannot use superconductors. So in the way of that developing the superconductor, there is another effect comes as a Zoser effect. This Zoser effect is that if we are placing a insulating, very thin insulating thing at in the way of conduct superconductor, then we are able to control the flow of current. Because the concept lies at here that when we are making this as a superconductor, that means resistance is zero. So this will be a king then. Then if we required a low current, then who will control that current? Because the resistance is zero. Okay. So this concept lies here. So we cannot until Joseph effect came into existence, we cannot use superconducting things. Okay, because superconductor means flow of current. There is no stopping of current. When there will be no stopping current, there is no control on the current because resistance is zero. Okay, so it is not used until Joseph effect was come. What Joseph effect saying? If we can place a insulating thing at here, a very thin insulating thing at here, then we are able to control this current. In such a way, we are able to control this current in such way, we can have a low value of current, we can have a high value of current, and we can have a superposition things in that current. Okay. I will not go in so much detail. It will require a good level of physics classes to understand how the superposition is going on there. Okay. So, but yeah, so in the superconducting, when the Joje effect is there, then there will be a superposition state of being current or not being current. Okay, because the only one punchline I can tell you here, because the current at here is not comprises only from the electrons. The current is not comprises only from electrons, because we know the current is comprises for the electron. So here the current is not, the electron is not only one carrier from where the current is made. There are another carriers, phonon carriers are there. So that's why we can suppose the superposition state at here. So the very first system is superconducting qubits. Okay, so we can make anything as a superconducting qubits. Okay, and how we can play? We can play by applying a Joseph effect, and by applying a microwaves kind of things. Okay. Obviously, when we are having a superconductors, so the gate speed or gate operation will be very fast in the superconducting qubits. So when the gate operations are very fast, and this is the reason because that in Goggle and in IBM, all are using a superconducting qubits currently. Okay. It doesn't mean that apart from the superconducting, uh, there is no development. No, yes, there are developments going on. We will talk about. Okay, so but currently IBM is using that superconducting qubits, and that's why because these superconducting qubits are required a very bulky arrangements of creating a 200 degrees Celsius to minus 250 degrees Celsius. This we have to create in the superconductors, right? So that's why their quantum computers are very bulky because they need special arrangements for this temperature maintenance. And this is not the temperature we are maintaining for a 1 minute, 2 minute, or 5 minutes. These are the temperature we have to maintain for a so much prolonged time to running a quantum circuit. Okay, so that's why IBM is charging now to run the quantum circuits. Okay, so Google Serac is also there. They are also maintaining that. So there is a latest. The IBM has started from the 20 qubits, and now they have moved to the 1000 qubits. So latestly 1024 qubits they have made this IBM, okay, and Google has reached up to only on 400 qubits. So this is a superconducting qubits. Along with the superconducting, it doesn't mean that superconducting alone superconducting effect will be there. Always there will be a effect called Meissner effect. There are the effect called Zeeman effect, which is there in the atomic level. Okay. So now we will talk about some atomic level things. In the atom, what happens in the atom? So we are talking about superconductor doesn't mean that we are only approaching these things to the negative temperature. There are hybrid things are also inside the atom. So inside the atom, what happens that electron, we know that electron is revolving around its orbit. And when the electron is revolving around its orbit, then we can make also. So see, we are not bounded by any rule that hardware engineers should adopt this rule. Because we are making a superconductor, so we should adopt a negative current or negative temperature rule. No, no. We can adopt any of the rule. So in this we can have a spin also. So spin means electron rotating. When electron is rotating, electron can rotate clockwise and anti-clockwise also. So when the electrons are rotating, so that means we can have this as a marker. This electron spin as a marker 0, this as a marker 1. Or we can have opposite. This as a 0, this as a 1. Okay. So so these things we can have as a marker. Now the question arises, now what happens to the superposition states? So for that, there is also a effect of physics for the superconducting states. So what is the effect? The effect is saying that whenever we are keeping this atom, when we are keeping this atom in the electromagnetic field, or you can say particularly in the magnetic field, then this atom's electron orientations are aligned in a certain directions. So suppose we are talking about ms that we have read in 11th or 12th, that is plus minus 1. Okay, so plus 1 we are assigning plus 1, we are assigning as a 1, minus 1 we are assigning as a 0. So now what happens to superposition state? So when we are applying the magnetic field here, then these atoms will align at the certain directions. So there are quantized directions. This is called quantized directions. So when these atoms, the same electrons, these same atoms are aligned in the different directions, we can name that a superposition states. So superposition states we can have in the application of magnetic field. This is one of the way I'm telling. There will be a several ways also. So we can have the quantized markers. But at here, we have to take a quantized marker. That quantized marker, on the basis, we can take it as a like this states. So this we can have a superposition. This we can have a superposition. We can have like this. So this I was talking about initially, that there will be between 0 and 1, there will be infinite possibilities of being 199 pair like that. But out of that infinite possibilities, how much possibilities we can realize in reality? So this is okay. So it looks like a very dirty image. So we can say, yeah, 0 and 1. Here the atoms are aligned. When we are providing a magnetic field, the atoms are aligned there. Okay. So atoms are aligned at this different directions. And these different directions, we can take it as a superposition states, because all these directions, the spin is between 0 and 1, clock and anti-clock. Okay. So, yeah, we was talking about these different possibilities, 199, 297, like that. So these different possibilities are of infinite, because we can always have a 2.1, we can always have a 2.001, like that. So that means these states are infinite theoretically, but how much that state superposition states we can realize, this is governed by this hardware. Okay, so this is the basic thing. So here, if we are able to resolve these states as, suppose, in a 7 or 8 superposition states, then in a 1 qubit we can have a 8 states only. In a 2 qubits we can have a 2 key power permutation combination of 7 or 8, like that states. So there are permutation combination we have to make it. After that is 8 states, and second that of 8 states, how much permutation combination we can make it. Okay. So along that, so there is a restriction from the hardware side, how much superposition states we can realize in a qubit, like that. So these are the things. These things we are combining with the superconducting qubits also. So there is, because in the hardware there is no rule. As much as you are getting the results, as much as there you are getting the you are getting the implementation, you are free to design. The matter is that how much cost it will take when we are designing. Okay, that is the restriction point of view for us. Okay, but for now, National Quantum Mission has been launched. So National Quantum Mission is saying that you just do design and develop and nothing else. Okay, yeah, if you can keep it on the eye on the rate also, so you can, but you can design. You have to design first. Okay, because if we are not having that multiple number of ways by which we can design the qubits. So then, in the National Quantum Mission, so this R&D is going on, that we have to discover multiple number of systems by which we can design a qubits, and by which we can realize the qubits in reality. Okay. So when we will have all these ways, then we can choose according to some criteria. Yeah, this one, and this one are fitting in our rates. This one or this one are fitting in our uh, speed point of view. This and this filters are fitting on certain other criteria. So first we will have a number of systems. So for that, we are developing. R&D is going on that. Okay. Yeah, fine. So the next category is coming to the trapped ion qubits. So trapped ion qubits. So ion, basically everybody knows that atom is there. When atom is having a, suppose, 3 electrons at here. Okay. Suppose 3 electrons are here. We know, everybody knows that atom are electrically neutral. Electrically neutral means number of protons are equal to the number of electrons. And if the number of electrons, some number of electrons are leaving, or number of electrons are coming, it is converted into the ion. This everybody knows. Okay. So so but this ion, if we are giving the energy to these ions, okay, so these ions are having the energy levels like this. Okay. And if we can give any amount of energy by any of the sources which is very readily available to us, like that, this microwave, laser. Laser is a good source of energy. So if we are having a good source of energy at here, so we can play with the energy levels of ions also. Okay. We can play these things in the superconductor also. We can play these things in any number of things. Neutral atom also we can play. But why we are choosing ion? There is a certain reason for that. So what is the reason for choosing this ionic? The reason is that if the neutral atom we are taking for this, if neutral atom we are taking on that, then there is a certain restriction that this neutral atom has to be kept in a certain vessel, has to be kept in a certain vessel. So in a certain vessel, when we are keeping this in a certain vessel, that means we are already disturbing the states, atomic state, because this vessel is in the touch with the surroundings, is interacting with the surroundings. Okay. So if we are making insulating surroundings, even then there is a chances of disturbing this atom. Okay. So this error will go on increasing. Okay, that is called a quantum error. Quantum error. What we are talking about? We are talking that we have set this superposition state. Suppose we have set these superposition state 1, 2, 3, 4, 5, 6, 7. Suppose we have set this 7 superposition state, but these states are very much sensitive, very much sensitive. If any certain 0.2 degree temperature of sudden outer temperature is there, then it will collapse. Suppose it will collapse like this. Okay. If any pressure is coming outside from the atmosphere, it will collapse. This is, I'm talking about the hardware side, physical. Okay. The physically it will collapse. This energy level will collapse. So these are the very sensitive things. Okay. So it has to be isolated from the atmosphere if we want a error-free quantum computation. So what we have to do, there is a one way of setting this apart from the vessel, that just suspend in a air. In a air you can say, or you can say in any atmosphere. So if we are able to suspend it, if we are this is the ion, if we are able to suspend it in a magnetic field, because this is ion, it has a charge. It has a charge. When it is having a charge, it can be it can be manipulated, or it can be altered without physical touching. Because we know when we are having some charge without physical touching, by putting some charge at here, in the vicinity of that, we can manipulate the energy levels, or we can manipulate the by having a magnetic field. So by application of electric and magnetic fields, by application of any energies, we are able to manipulate this charging state. Okay. So when we are applying magnetic field or electric fields, so electromagnetic field we can call it. So then this can be suspended in a freely state, in free state. So that's why we are choosing this as a ionic state or charge state. We can also say this charge state. Okay. So ion is basically means when electron is leaving or is accepting the electron, that is the ion, or positive or cathode or negative ions. So that is the things. These are the basic of trapped ion qubits. So we have trapped the ions at here and in the magnetic field or in the electric field, and we are manipulating. How to manipulate? How to control the things? By giving the laser light. So by laser light we can control. By microwave light we can control. Okay, these are the ways which we can control very easily. And in having these qubits, when we are having this type of qubits, then what to choose 0 and 1? So we can choose 0 and 1 because we know that this is ion and can have the energy states like that. So when ion can have the energy states, so any of the energy state we can have a 0 and 1 according to our convenience. So what energy state we will choose? It depends on how we can manipulate. Suppose if we are choosing a high level energy states, then high level energy states are more prone to be disturbed because the energy is high. If the more energy is high, then there is a more internal energy which prone to be interact with the atmosphere. So that is likely to be disturbed. So better to choose from the lower energy levels. But if we are choosing the lower energy level, then there is a motion of inertia of rest. Then if we are choosing lower energy states, then we have to provide a sufficient energy to this. Because this is already in the lower energy state, ground state, we have to provide a sufficient energy. So there are drawbacks and there are benefits also. Upper energy states, if we choose, we will have prone to be more errors. Lower energy level will be choose, we are prone to be investing a lot of energy in it. So to work on the qubits, if we want to work on the qubits, we have to activate these qubits. To activate these qubits, we have to control, and this controlling is prone to be having a good amount of energy. So that is a trapped ion technology. So to realize 0 and 1, how to realize the superposition states? Also same way, by applying the magnetic field, because ions means ions having the atoms. Then atoms, that mean the same principle we can apply. Okay. So we can kept in a magnetic field. It will resolve in the this will resolve in the quantized energy states. Okay. So this is called IGNS. These are the schemes to split in the multiple energy levels. So these are the trapped ion qubits we are realizing. So these trapped ion qubits, or we can say spin ion qubits, there are some company list. I'm having this. One of the startup was Honeywell, which is having a system models. So they are running on this ion trapped qubits. So one company is of Honeywell. That is, I'm reminding. It is having a. It is started from the 10 qubits, and it is commercially available. I have not checked this fact, but yeah, on the net it was showing that it is commercially available for the 10 qubits. For the 10 qubits is so much small, so we cannot have a good programming at here. So even in the Shor's algorithm, we required 18 or 15 qubits at least, because multiple things we have to input there. Okay, so that Honeywell is also using that. There is also one. This is one company. The second company is also that Quantum. That's Quantinon. This company is are already using the ion trap technology in developing the quantum computer. Okay, so this is also the I think Cambridge University collaboration it is having, and its processor series is running in H series, that is hybrid series. Okay, so they are planning to have a 56 qubit quantum computer, and because this quantum computer, I have heard this news, it is in collaboration with the Cambridge University, so maybe it will reach on this landmark 56 qubit. Already, although we are talking about 10 qubits and 56 qubit of realization, but see the IBM has marked the figure of highest number of qubits. They have reached on this. Yeah, and this is a real quantum computation they have reached on their server. All of you can go on the IBM server and make an account. I suggested you all of you. Okay, so but the trap ion qubit are lacking with scalability. The trap ion qubits are lacking with the scalability. What is the reason for scalability? Because we can trap the ions at here, we can trap the ions at here, we can trap the ions at here. 2, 3, 4, 5, 6, 10, a small number of ions. It's okay. We are trapping and we are applying a magnetic field. So there is two ways. Suppose we are applying a magnetic field, each qubit separate, then there will be a too much bulky things. Okay. And there is a one way, then we can apply a strong magnetic field and keep it all the ions at here. We can apply a magnetic field strong and we can keep the ions in between of that. Then there will be an error will be there that it will, because it is charged, this is a charged one, it will infuse this one, it will infuse this one, or there are chances it will diffuse this one, interfere this one. So the chances of errors are there as we move towards the larger level of uh, this trapped ion qubits. And of course, there are solutions for every problem. So maybe I can't say furthermore than what are the solutions with the Cambridge University along with the continent that driving there. So maybe they are able to reach out or to overcome that scalability problem. They are able to separate these things in a chamber or whatever. I don't know. So they can have a, but they are announced that they can have a 56 qubit. They are eyeing on this. Okay. So, so, so another now, these are that for the trapped. Now, this photonic qubits. Yeah, this is running a very good R&D at here because there are a lot of scope at here. The reason is there. This is room temperature working. Okay, so the photonic qubit and the superposition. Why it is saying that photonic qubit can lead the quantum computation. The reason behind that is the idea of the quantum computation itself comes from the photons. Okay, so because I discussed this in first day that de Broglie, this was the idea for the quantum computation. Means this was the principle. Okay, what principle that particle can behave as a wave. Okay, and that principle comes from the photon itself. So we are particle photon as a wave as sometimes by the Newton. Okay. So that Newton or photon is itself a particle. But but we know that light is a wave. So so the resolution was that both are there. Right. So the initiation of the quantum computation from that point also. So this photonic qubit, I think it's a frequency will match. Why? Because the basic principle are same in developing the quantum computation and the photonic qubits. So when the basic principle are same, so it will lie in the very great bandwidth of the window, so that we can develop the photonic qubits. The second benefit is that it is room temperature. It is operating in the room temperature. As IBM is working on the minus 200 all these temperatures, but here we can manage all the things in the room temperature. Now, the most important thing is how to do the markers for that. So previously we are having the markers by splitting this atom in a multiple quantization like that, 0 and 1 superposition. But at here there is no concept of atom. We don't have to go on the atomic level. Okay, so we have to play for the light waves, only light waves coding we have to play, right? So all this what we are hearing now, okay, photonic qubits are very much easy. Yes, very much easy. So they are very much prone to be scalable, very much prone to be developed at the room temperature, and very much prone to be developed um, in the current manufacturing facilities. Okay, this is also the uh, restriction that all the labs, all the companies are creating, Intel, NVIDIA, all the semiconductor companies that are having a million or billion of crores of investment in their existing manufacturing plant. So suddenly we are saying that we are coming with a new technology which works on the different machines. So to implement that technology, we need a different machine. So so suddenly all of a sudden nothing will change. Okay. So that means every company has to see the investment point of view, has to see the infrastructure point of view, has to build the things slowly and slowly and slowly. So photonic qubits are building, but the things are need to be aligned with present manufacturing facilities. Okay. So how to realize the markers here? See, we have to see the markers first. Whatever the system we are seeing, we have to see the markers first. Okay, so that is the main point to include this hardware at here. Okay, so you can have a things that superconducting qubits, trap and qubits, photonic qubits like that. But if you are not able to identify the markers, then it means your knowledge is insufficient in that hardware side. So to be a good quantum computation expert, you have to be a knowledge for all these things. So photonic qubits, in the photonic qubit, how to implement that markers? 0, 1, superposition. Photons have to go on the markers 0, 1, and superposition. As I said, the photonic is basically based on the same logic, a same principle where the quantum computation has initiated. That means the light. Okay. So in the light, we are having a different phenomena. Light is having a phenomena of reflection. Light having a phenomena of refraction. Light having a phenomena of polarization also. Polarization. So any of the process we can take it as a marker. So suppose we have, suppose we are taking reflection. So in reflection, the light is incident on the surface and it's going on like that. Okay. So in the reflection, only and only one wave is there. See, in the reflection. Okay. The light is coming. This is the input. This is the input. But in the output, we are having this only and only one. So we cannot implement this reflection as a marker because only one thing is there. Like in the refraction, light is coming and rays is going on this transmission. So there is only one output there. So now here also we cannot take as a reflection. But it doesn't mean the reflection is out of the window. Okay. Yeah, alone reflection, we cannot take it. Okay. Yeah. What we can take it? There are surfaces which are going simultaneously reflection and refraction. Yes, we are seeing this in our daily life. We are seeing in any or commercial buildings that glass we are able to see our image also as a mirror, and that glass we are able to see the transparency also. So that means simultaneously the reflection is occurring on, simultaneously the transmission and this refraction is occurring on. Both the things are occurring simultaneously, right? So that means any of the thing we can mark as a 0, any of the thing we can mark as a 1. And simultaneously, yes, now simultaneously, depending upon the place where we are polishing the things, we can increase the intensity. We can increase the probability of being 0. We can increase the intensity, or we can decrease the intensity of reflected one. So that means we have the window to manipulate these things, play between 0 and 1, possibility of 0 and 1, finding the possibility in 0 and 1, reflection and refraction. So that means we can have this system as a design qubit. I'm telling you the possibilities, how we can design. Okay. See, this is a very new field, and if I will include only that things that has been implemented only, that means we are restricting our development. So everyone, I'm saying to everybody is okay. This is not a wise interaction. If there would be a wise interaction, then I'm saying everybody's just come up with the ideas. Yeah, we can. Any idea can be implemented in there, and the quantum computation development requires everyone ideas. So from the student sides to from faculty sides to from industry side, anyone can have give an idea, and what idea they can give how we can take it as a marker and how we can control it. So two things we required: how we can take it as a marker of 0, how we can take it as a marker of 1, how we can take it as a marker of superpositions, how we can make a superposition, and the second thing is that how we can manipulate, how we can control between 0 and 1, 1 to superpositions by any other sources, by laser or by something. We have to do these things also. So anybody can come up with the ideas. National Quantum Mission has been launched. Just go to the all of your faculties and I think all of your departments. Uh, there will be a grantings and fundings. Just demand for the grant and from the National Quantum Missions and just try to develop all these things along with the software side. Yeah. If you are from the CS, then along with then develop these things, collaborate with the hardware side department, EC departments, physics department, combined EC, physics, and all this CS department, and develop the quantum computation. Go for the quantum computation. We need it. Why we need it? There is a very much apart from the development issue, there is a very much international politics issue. Okay, so on the international fronts, we need the quantum computation because there is a race from China to USA to developed countries to the undeveloped countries. Whoever will build a this quantum computation, who will win this overall international things, the supremacy. Okay, so suppose there is a news in the media that China has developed this supercomputation, quantum computation, but we cannot believe because China is restricting any privacy, okay, to go on the public. So because there is a super applications of this quantum computation, if we are having this quantum computation developed, hardware developed, ready here, then we can solve the drug problems. We can solve the multiple level problems where we requires a good complexity space of resources. Okay. So yes, so I think you have understood the game of markers. So I'm telling because frankly speaking, I have worked on the photonic devices. That means these photonic qubits. Okay, rest of the system didn't work, but yeah, I worked on the photonic devices. That's why I'm saying there are 100 possibilities. Any word can come up. Okay, so whatever I'm meeting with all the faculties. I'm meeting with the industrial levels. So I'm saying just give their thoughts. So I will also request all of you give their thoughts, hear your thoughts. Okay, so in a random manner. So nobody knows what thought will come at here, and we were able to develop that thought to the quantum computation. Uh, yes. Now coming to the polarization. So polarization. So this is from the point of view of reflection and refraction. Although this is not being used in the industry, but yeah, I tried to use it, but unfortunately from the funding size, I dropped that idea. But yeah, it can be developed. So on the polarization side, mostly this polarization is used in the industry. So on the polarization side, what are the markers? So polarization, we know that the light is the electromagnetic fields, and in electromagnetic field, the electric and magnetic fields are perpendicular to each other, like that. And the magnetic field is nothing. There is magnetic field is the virtual thing, right? So if we'll go on depth, then there is only and only electric field in this thing. The electric field changes electric field, develop the magnetic field. Okay. So in the light, there are random directions of the polarization of electric field, like that. Electric field is oscillating like this, oscillating like this, oscillating like this. Okay. So everybody knows if you are reminding class 12th knowledge. Okay. The polarization of the that means the electric field vector lies and oscillate between this direction, between this like this, or between this. So there are random directions. There are random directions. Okay. So we can form it like this. Full of wheel. Okay, there are random directions. Okay. So if if we can make the marker here also. Suppose we are making a marker this vertical and horizontal. Okay. So we are seizing everything. We are seizing every vibration beside this. That means there will be only a vertical direction, vertical level vibrations in the electric field. So suppose we can mark it as a 0. And in another direction, we can have a polarization. Suppose this, we can mark it as a 1. So then along with these directions, we can mark it as a 0 and 1. Okay. So in these directions, so now you can argue. So there are the arguments, because previously we were saying that there is a zero point 0.5 and 1. So in between 0.5 and, oh sorry, 0 and 1, in between 0 and 1, 0.5 cannot be taken as superposition. So how we are taking this 0 and 1 and this as a superposition? Because this was a absolute value, mathematical value. This is not the absolute value. These are the intensities. These are the light. These are the intensity. The hardware implementation is completely different. These are the light. So light having a different intensity at here, different intensity at here. But at here, it will have a mix of intensities of this one and this one. So that's why I'm telling in between, we are having superposition. So that's why I'm telling the things are completely changed. So same scenario at here, same scenario at, but things are completely changed when we are changing the systems. So these are the superposition things. We can take it as a polarization, as a marker. How to control? The control is very simple. The polarization, we know the polarizations are coming. The lot of polarizers are coming in the market. Okay. So we are seeing these things in our lenses, our eyeglasses. We are seeing the polarization things. So chromatic lens, photochromatic lens, all these are using this polarization principle. So these are very, very simple things. Okay. So we can have a markers in a very simple way. Okay. So that makes a window to having a scalability in the photonic qubits. So this is two of the markers we have discussed. So if we are going on the if we can have out these things like photon or light. Photon means light. So light is also having a two path. Suppose we are placing a half mirror at here in the light's path. Suppose light is coming at here, we are placing a mirror at here. So when we are placing a mirror at here, the photon will come in this direction, some photon will go in this direction, like that. And if we are collecting at here, and this another mirror will be there, we are collecting these, it will have a superposition. If it is not clear, then with the dirty, with a neat and clean figure, we can understand like this. The light waves are coming like this, and we are placing a mirror. So when we are placing a mirror, some will go like this, some will reflect like this. So at here, we will again place a mirror, some will go like this, some will go like this. So here we will place a mirror, will go like this. So these things will meet it. So this we will mark as a 0, this we will mark as a 1. And when they are meeting, it's a very simple principle. Okay, nothing to worry about. So when they are meeting, so we can say there is a superposition of 0 and 1, superposition states, right? So these are the markers we can mark it at here. So any of the system, everybody is free to adopt their systems. Any of the system, we can make it as a marker and we can develop that thing in a scalable way. So these are the photonic qubits. We are playing around that. And the very important attribute it is having, it can work in a room temperature. Because light can work in a room temperature. So this is a very much scope, and a lot of photonic devices have been developed in the last 10 years, last decades. Okay. So there is a very much scope for the photonic. So now, so for the photonics, so there is companies, startup companies. There is a company called one company that is called Quandela, Quandela company. That company, I think, which is that's from the France, I think. Okay, so that are used the cloud. Sorry, that has used the cloud-based chip, the architecture. Okay, and in 2007, I think yes, yeah, there are 10 years, 9 years of this company. So they have announced in that also 2017. They have announced when they have launched this company, they have announced they will develop a full stack, a cloud-based chip for that. So they are using a six. At that time, they are using a six photonic qubits. So six photonic qubits and developing. Last year, I have heard the news that they have developed the 12 qubits, photonic qubits to quantum computation, and this latest development is that they have developed the 24 qubits. Okay. So, but this 24 qubit is in the dark. So, because of the marketing strategy, they have spread the news. They have 24 qubits, but it is in the dark. Right. So, yeah, commercially they are very. Their planning is to avail the things to the commercially, but I have checked. I have brought the quotation for that, but they have not given any quotation for this. So that means from my side, there is a declaration they are not developing uh, the commercial computation, quantum computation. Second, there is a this is a very big name now developing Xanadu that belongs for the Canada. That belongs for the Canada, and it is a very big major player going to be very big major player in this developing the quantum computation. Very major player when he wants to develop the quantum computation. Why? His processor. He has launched the processor. That processor is called Arosa. Okay, and it was having a 12 qubit computation. Yes, it is developing and the photonic based. Why photonic? You know, we need the room temperature. Then there must be a question in everybody's mind: when we can develop the room temperature, then why IBM is a foolish? Why IBM is going on the superconducting qubits? No, that is the reason for that. We will tell you in the end. So and the yes, there are commercially available. There is a news. I have received the quotation from that. There is commercial available computation inside the Zendo. Right. So they are using basically silicon based. They are using basically silicon based chips for the photonics. Okay. And why we are saying that it's a major player? They have collaborated with the five universities for the development of the hardware, and that five from the five that universities, they are coming with the collaboration, and they have announced that they are going to develop a 1 million qubit quantum computation. So this 1 million qubit, IBM has reached only 1,000 qubit till 10 years, in 10 years, not a 10 years, in the span of 8 years, I'll say. But this is announced with the five university collaboration. This is announced they will develop the 1 million qubit. And they can develop because this is my thinking also that photonic qubit can win the race among all the systems. Okay. There is one qubit system also. We will talk about the Microsoft is working from the last decades, 1.5 decades. So that is not being implemented. So this why this is going to be a very major player. The shares are going very high because this is going to be developed 1 million qubits quantum computation. And if it is going to the develop a 1 million qubit quantum computation, that means a lot of countries will be behind that. First, USA will demand, China will demand, okay, and there is an international behind this who will supply this quantum computation. As there is a international politics who are supplying the nowadays this defense equipments. Okay, so like that. So there's a political issues, international political issues to developing that thing. There is a one more company of USA. They also developing, and they are funded by the US government. That is quantum computation. So they are also developing in the USA, but USA is not revealing the exact status of this. Okay, but yeah, USA is also in the race. Maybe they have half developed, or maybe not. So, that is from the photonic qubits. Now there are one more qubits, the neutral atom qubits, but these neutral atom qubits are rare to be developing in stage. Okay, neutral atom qubits is the one I can give you one example. There is NV. So the example is NV diamond. In the NV diamond, the basic thing is that it will be a neutral. It based on the principle of mechanical principles, based on the principle of stress and strain, based on the principle of uh, metallurgical logics. So it is not based on the charge. Okay. So what happens in the NV means N stands for nitrogen and V for vacancy. So what happens actually it starts from the diamond. What happens in the diamond? In the diamond, we know that everything is made up from the carbon. So there is chain of the carbon in the diamond, like that. And these chains are so much connected each other, so it makes this connections, interbonding makes the diamond very hard. Okay, so they are not prone to be discarded. So what we are doing, first we are inserting in this matrix, we are inserting a nitrogen atom. So in this matrix, we are first inserting the nitrogen atom. And when this nitrogen atom are going inside this matrix, what will happen? There is no space because it is already so much hard. So there will be no space diamond inside the matrix of the diamond. So it is also so much hard. So when nitrogen is going inside the diamond, it will create extra stress for these bondings. And this extra is because of that extra stress, it will prone to be in the flexible or changing state. There is a very basic principle. So if you are standing somewhere, then you are prone to be stand at there, no problem. But if there is a storm or something else there, stress is there, that means you are prone to be change your position. So that's it. That is disturbing their state. Okay, so same thing is here. So they are going to change the position. So that means when they are inserting the stress is there, they are going to change the configuration. Now, in the same time, we are extracting one of the carbon atom from the lattice. So when we are extracting one of the carbon atom from the lattice, so we are creating a vacancy in it. So by creating a vacancy, we are relaxing this stress. Okay, so by creating an unnecessary nitrogen, we are creating a stress. Now we are removing the carbon atom. So this removal of carbon atom is relaxing from this stress. So when it is relaxing from the stress, now what happens? There is a vacancy created at here. When this vacancy is created at here, so it is prone to be changes. In the same time, this vacancy is rotating. This nitrogen is rotating, and whenever this nitrogen and vacancies come together, whenever nitrogen and vacancy comes together, it observes. It is a predefined. It is not made for the quantum computation. All the effects are predefined. So it is an effect that when nitrogen and vacancies are coming together, it is working as a artificial atom. So it is working as a artificial atom. So when it is working as an artificial atom, now we can treat as just like as we were treating in the superconducting, as we were treating in applying a magnetic field and giving the energy like that. But the main thing is that now we can play with the atom. This is artificial atom, and this artificial atom we have made at a room temperature. Okay, and to play with this atom, we need not to be go inside the atom. We are not going inside the atom. Only nitrogen is there, only vacancy is there. So they are worked as an artificial atom. Only we have to control these things. And to control that things, either we can apply a magnetic field or we can apply electric field or we can have a laser source to giving the energy for this. Okay. So we can have the changing states, same markers 0 and 1 superpositions. By applying magnetic field, it will quantize when it is working as an artificial atom. It's the case. Now return to this. The same thing, we can quantize this energy levels. When we are quantizing this energy level, we can have a marker of 0, 1 and superposition states. So that is from the NV qubit sides. Okay. So in the NV qubits, there are a lot of development is also going on because NV qubit is also a scalable. And the NV qubit is also a scalable one. So basically, For the NV qubits, we can have this play MS as we are playing in the atom. Okay. So in the atom, we are playing with the spin of the electron. At here also, we are creating artificial atom. We can play with the spin of the electron at here also. So this is like that. And now, there is one company I have heard also about that the electron 6, the electron 6, that is a startup that is working on that, and we centers, and there is another company, Envision. This Envision is also working on that, but there is a scaling issue they are facing, and multi-qubit is a challenge in that also. One thing in the NV center, NV diamond qubit is that it will involve the complexity when we are having uh, scaling the large number of qubits. Because when we are having a large number of qubits, then all the nitrogen and vacancies. Which nitrogen, which vacancies? Suppose two nitrogen are coming to the vacancy, then one nitrogen can come to the two vacancies. That will create a high misleading markers. Okay. So misleading marker means maybe this is converted to the marker of 001. Maybe this is converted to the marker of 010. So it will leave the false thing. So that is the scalable issue. The complexity as will go on, the more qubits, the complexity will involve. So we are talking about all these systems. So all these systems are running with the drawbacks and the benefit, but it doesn't mean that we are not having the reality of the quantum computation. At somewhere, some corners, all of the companies, all of the industries are working on that, and along with the collaboration with the academic institutions also. So with the universities also. Okay. So in India also, all the IITs, all the NITs, BITS, all the state level universities, and all the nowadays the private universities are very much higher. So they have the very good infrastructure. They have the very good infrastructure for the research also. So they are also on the collaboration side, because nowadays they are having the faculties of quality faculties, right? So all are contributing on this. So if we are talking about and keep in mind that all these things we are not talking about a 5 or 10 or decades ago. All these factors, all these facts we are talking about in a 4 or 5 year development. So that means it prompts to be changed. Okay. So when we are working on the nanomaterials, when we are working on some other hardware, so we know that this is a fixed rule. We cannot change it. But here there is no fixed rule. There is no fixed rule. Okay. Maybe after 5 p.m., 6 p.m., you will read on the net. Oh, I was telling about this thing, but this is not the so. Maybe a news can come in a 1 hour. So all these things are possibilities, pros and cons, and we are discussing it here, but it doesn't mean we cannot develop all these things with the scalability. Somewhere, some corner, something are missing. So we have the 6 criteria, suppose. So some of the system is completing the 2 criteria only. Some of the system is completing 3 criteria only. Some of the system is completing a 1 criteria only. Or like that. So these are the pros and cons. So we have to come together. We have to combine ourselves, and we have to see where by combining all these approaches, maybe hybrid approaches, we are able to develop this quantum computation, quantum computer hardware. Okay. So the things are going on very fast way, very fast way. So with this approach, also India, the National Quantum Mission has been launched before 6 months, and after the quantum mission has been launched, the work is going on a very fast way. I'm seeing there is a much because in the I'm seeing this development before the 4 or 5 years. There are very rare expert of the quantum computation. Okay, very rare expert of the quantum computation, apart from the IIT's faculties or NIT faculties or some industrial professionals. Okay, but I'm seeing here there are a lot of things, lot of potential coming here. Because why they are coming here? Because MHRDs, UGC, all have given the permission to to mm, bringing the projects from the quantum computation. They have developed the quantum computation. So they are developing the quantum computations. They are having the projects. The faculties are now having the projects. Okay. Maybe a small projects, it doesn't matter. There's somebody having a 10 lakh project, somebody having a 1 crore project. So it doesn't matter. The matter is that they are involving their minds in developing the these qubits, in developing the integrating the qubits. So see, to develop the qubit is not the part of the quantum computation. So along with that, we have also have to develop the full pipeline. Suppose we have developed the qubit, yeah, also it covers a 70% or 60% of work. But when we are developing the qubit, we have to develop the qubit, the path of the qubit, where has to go, the realization of the qubit, interfacing of the qubits to the programming or algorithm. All that we have to develop. We have to develop the pipeline. That means we are in the need of not from the hardware side. We are in the need of hardware also, algorithm also. We are in the need of electronic and communication engineer for the communication also. That means that is the work of all together, right? So, okay, I'm talking about the qubit only, but it doesn't mean the qubit makes all the quantum computation. It forms the basic, but everybody's contribution is required to develop the sort this quantum computation. So overall, so that is the scenario. Now we are coming to the next qubit. Yeah. So silicon spin qubits. So these are the latest one. So before that, moving to the silicon spin qubits, we have to talk about. I want to talk about some error point of views, quantum error corrections. Okay. So actually, what happens as we have discussed that from the temperature, from any variable, suppose pressure, okay, or anything else, or current, or whatever, okay. So not the current, then atomic charges, or anything. The charges may be greater or less. So whatever, if we are disturbing these things, then we have to disturb the qubit, because we are playing with atomic level. If we are not playing with the atomic level, we are creating artificial atom. If we are not creating that artificial atom, that means we are playing with the photonic qubits. Okay. So all these systems are differing from each of the criteria levels. So what differing? Superconducting, it's a very much typical. Superconducting, 200 degree, minus 200 degrees Celsius temperature is very much typical. So they are very prone to be disturbed on the disturbing stage. Okay, that is called a perturbation. Okay, so in quantum we are calling it a perturbation. So they are very prone to be perturbed. The trap ion qubits, they are also very prone to be scalable issue. Okay, so it can have the very good efficiency, but it will all have the scalable issue. The photonic qubits, the very much the right candidate, potential candidate in the coming technology. The things that it can be developed at the room temperature. Apart from this, I forget to write it here. It is scalable because it's a photonic. Apart from that, it is more prone to be having errors, because we are not creating a super hypo type of environment right here. Not creating a 200 like that. Not creating a trap ion environment. So ion can be trapped. It is not touching with the vessels. Okay. So, but apart from all these things, there is a one thing which is called coherence time. So, coherence and decoherence, this is a very essential criteria of these qubits. So, the coherence time is that time on which the superposition states are remained superposition in the superposition. So, suppose we were talking about the atom. So, atom was quantized in different directions. We are assigning this as superposition states. Okay, then the coherence time means we have distributed a 0 1 state at here at this. Okay, okay, let's be very clear. So this is a thing. So we have distributed, suppose these are the quantized state. We have distributed 00 state at here. We have distributed 10 state at here. Cat 10, cat 00. Okay. And suppose this state we have distributed a Bell state, entangled state. Okay. So that is 00 plus 10 like that. So when we have created this and we are running algorithm, or we are running a not algorithm, maybe we can call it a circuit. We are running a circuit. So the circuit can be run. The circuit can be run only when these labels are at their own state for a prolonged time. Okay, so these quantized states should remain as it is for the prolonged time. But what happens in the atom, there is a natural phenomena. As soon as a magnetic field will get disrupted, then if there is a 0.001% disturbance in the magnetic field, or there is a 0.004% or extra source of energy is coming there in the atom, then that can merge in each other. That can merge in each other. Okay. So suppose this is the atom. We have created a magnetic field at here, and we have distributed this in quantized state. And suppose from any other source, whatever, a temperature or any other source, laser, or uh, any pressure, whatever is the source, suppose an energy is coming at here, or energy is withdrawing from here, or there is any change in energy, that can collapse these things, because this is very much prone to be collapsing. So if they will collapse these things, then you are saying that my friend is running on this path and another friend is running in this path. You are saying, okay, just collapse these things. So how can the program can run? Okay. So that the program or algorithm, whatever the circuits we are being made, the quantum computation will be stopped there. So this is called the coherence time. So the time till when we are able to resolve this quantized, to remain this as a quantized. Okay. So that is a coherence time. So that is a very important parameter. How much coherence time and related to the error. Yes, related to the error. If the coherence time is disturbed, we are prone to be error. And this error is of two types. Suppose if there is an error, so maybe one is called bit type error, flip. Another is called phase bit error. Okay. Another type of errors can become. This I am defining on the based on the two gates. Okay. Suppose this was working as a somewhere another gate, and suppose because of the disturbance, it is working as a X gate. If it is working as a X gate, at randomly I am choosing. There is no logic for the decision. At randomly the errors is come. Suppose at randomly it is working as a X gate. So when at randomly it is working as a X gate, so every input, whatever we are getting, suppose we are getting input 0. So if in the normal position, but because of the error, it is working as a X gate. So instead of 0, we will get a 1. So how to rectify that? If we are able to recognize that we are flipping everything is flipping here. So that means we can rectify this by applying additional X gate, another, right? So like that phase gate, when suddenly it appears, it seems to be appear to be applied a Z gate at here by the sequence of consequence of this error. Suppose a Z gate is applying at here, operation is like that. The Z gate is applying, then it is called a phase bit error. Then we have to rectify this phase bit error by applying the consequences of X, Y, Z gate or whatever. Okay, or maybe a Z in reverse order, or maybe a C naught gate. So we have to rectify by applying this. This can be rectified only from the one gate. This has to be rectified by applying a different gates, combination of gates. There may be anything error. There may be S gate can be long like that. Error can also leading to the Hadamard gate. So the solution for the Hadamard error rectification is very much simple. We can apply another Hadamard gate. Okay. So these type of things are reading in the quantum error correction. So this is another thing. This part is carrying quantum error correction. Okay, how to correct these errors? But when the errors are coming, so it is not like that errors are coming. That means it's giving faulty things. If errors are coming, we can have the quantum error correction. But for that quantum error correction, even we need the extra qubits. Even we need some extra qubits. So suppose we have the work for the 50 qubits, any algorithm that needs a 50 qubits, but for the sake of clarity of the safety, we need additional 10 qubits for this quantum error correction. So that means if any algorithm is needing a 50 qubits, so now they are needing a 60 qubit of quantum bits, qubits, you can say. Okay. So this how this quantum error correction or errors are working that. So coherence time. So overall, yeah, we have initiated this discussion for the coherence time. So I think you have understood for the coherence time. So decoherence time is the same, where all the things, all the states are merged. That is called the decoherence time. Okay. So these coherence or decoherence are the important parameters for that. Now coming to the this topological qubits. So in that, sorry, silicon spin qubits. In the silicon spin qubits, that is that I was talking about, industry need not to be changed their infrastructure. So, so this is the effort from the industry side also, uh, that they have they are saying that we don't have to change our infrastructure. So they have developed these silicon spin qubits, because nowadays semiconductor are running on the silicon industries, semiconductor industry running on the silicon. Some of them shifted to the this germanium silicon, but that now running on the silicon. So they are thinking that they can anyhow they can have a same infrastructure. For that, this effort comes from, that is, they can now be have as a silicon spin qubit. So as the name suggests, there is a spin based marker. The spin based marker means spin ms, that is same thing. The ms plus 1 or ms minus 1. The spin based marker we can have. But that spin based marker we have to realize in a silicon itself, in the silicon itself. So there are three methodologies in the silicon. First methodology deals with that silicon can have a semiconductor. So when silicon have a energy band gap, right? So the electrons in the conduction band, sorry, this is the valence band, electron in the valence band, electron in the conduction band can treat as a marker for 0 and 1, or electron in the Fermi level, we can treat is the Fermi level as at this level of Fermi level at is this marker also. Now the thing is like only it was lacking behind from the superposition state. So that was the level of effort the industries are putting that here, that anyhow we can have the marker for the superposition state. So yes, we can have the marker for the superposition state if anyhow we can create this silicon from the top to bottom, bottom to So there are two approaches, top to bottom and bottom to top approaches of creating semiconductors. So one approach is creating vapors, then vapors, and then vapor. Another stage is that we are having a quartz. We can cut the quartz and we are reaching on the semiconductor level. So this approach is called the top to bottom. This approach is called the bottom to top. So in these approaches, the this superposition concept is lies. Okay, so they can have the marker of the superposition states on these approaches. Let me see. Something is there. 1 minute. So the topological qubits. These topological qubits, topological means symmetry. 1 minute, let me have this. So topological qubits. So there is a one system we can work on that. The topological qubits are topological means symmetry, a shape, a change of shape, or symmetry and shapes. So we have to play with the symmetry and shapes for the topological type of components. So uh, the Microsoft is working on that. This is the very future technology. If we are able to make it this technology, this Microsoft is working on that on the last 1.5 decade, that if we are able to make this technology, then every problem will be solved from this all these above qubits. Because in all the above qubits, somewhere some some qubits are lacking behind to some are lacking behind from the error issues, some are lacking from the noise issue, like that. Some are lacking behind inference issues, okay, and some are lacking behind from the cost or economical cost issues, okay. So what is this technology? So this technology they have observed that I will not name, otherwise it will confuse. They have observed that there is uh, some particle. Microsoft has observed, they have read about development in the physics, in the particle physics. The development was going on around the particle and antiparticles in the world. So every particle has the antiparticle. So they are saying that there is a one paper of Nature which is saying that there is a one type of particle which is itself has the antiparticle, which is itself has the antiparticle, and that particle is found on the edges of any, this is found on the edges of any superconducting things, okay. So what is the speciality of these particles? The speciality of these particles are there that if these particles are combined together, if these particles are combined together, then when these two particles are combined together, then by mixing and intermixing, they are forming a diamond-like structure. Diamond-like structure means not resemble to the diamond. Diamond-like structure is strength or this you can say that pro ability not to be changed, because diamond has the ability not to be changed. So that attribute it will develop in itself when we are mixing that type of particles at here. So that particles, the Microsoft are naming that technology, and these topological qubits are error free. Why they are error free? Because they are not able to change on interacting with the atmosphere. Now, I want to emphasize this fact also, that because we are all on all the qubit system, we are saying that we are prone to be changed by the noise. So the peoples can ask then that is there any method to separate the noise? So there is, if we will have that method, we will have that technology that we can separate the noise. But even then, what happens in the quantum system, that when the quantum system we are measuring, okay, we can have the separate things in the quantum computation. Yes, we can have the separate things. But when we have to measure these states, when we have to measure these states, we have to interact with the outer atmosphere. Okay. So when we are computer, so we have to disturb the things. We have to disturb. So anyhow, this error we cannot eliminate, but we can have the technology so that the domination of that error can be neglected. So we can preserve the structure, whatever the errors it will have, the error. So this type of things, the whatever the errors it will have, errors will have the outer envelope, not on the inner structure side. So markers, so for the any structure, we can mark 0, and any one structure we can mark. Any of the other structure, there are a lot of structures inside it, we can mark 00 or 01. And the main thing is that these structures are not going to be changed when we are interacting with the atmosphere. Okay. So that is from side. And so these are the company list. If anybody wants, then they can take from the LMS. So all these things I have discussed. So the recent milestone. So this is the fact that neutral atom array exceeding 6,000 atoms for the programmable systems that has been discovered. Okay. Then this is the summary of latest research paper. I have summarized here the trapped ion system now achieving the gate errors now below than the 10 to the power minus 7. The superconducting multi-chip modular process, the superconducting multi-chip, the superconducting what happens nowadays? IBM has launching 1,000 qubits, but in the 1,000 qubits they have launched the processor. The processors named are like that Cyro and all system, but that system having only a one or two chips. But now that multi-chip modular processes have been developed. Okay. And in the photonic system, the boson sampling breakthrough. What is the boson sampling? Boson sampling, it lies on the particle side. There are Einstein boson statics, and uh, there are polystatics. Then the particles which are following the Einstein boson statics, that is called the boson system. Boson systems are these are the systems which are basically based on spin. The spins whose spins are same, calling it Einstein bons, whose spins are different, calling it another category. So that boson sampling breakthrough has been made. What happens in that breakthrough? We can have the chances of superposition state. Okay, so that things. So from the algorithm side, there is a variational algorithm for the chemistry. We will discuss in more. Yeah, for the application side, you see. Uh, we were talking about chemistry now. That yes. So the very vast application is from the chemistry side because this world is coming from the materials. The materials are from the atoms, molecules. The molecules and atoms, right? And when we are seeing any material, any matter, so on the front side, we are seeing it is made up of molecules. So this molecule are arranged in some pattern and having some bondings. Okay. So what angle there is a bond between oxygen bond and hydrogen bond? What bonding is there? And at changing, suppose it is having a 69-degree angle in the bond. So can we have this bond at the 68-degree, or can we have this bond at 50-degree? If we can have, then what will be the structure for that? If we are changing the angle, the structure will also change. So all these parameters, so when we are going in the molecular side, or we can say the intention is go on the are made up of the molecules. So when we are going on the molecular side, we have several parameters, million of parameters. That at 1 degree, there will be a million of parameters changing. So you can estimate at 9 degree or 10 degree, if we are going on 0.1 degree to like that, there are how much permutations of combinations. So for all that combination, we cannot go for the classical computation. So all that parameters, we require such a system who can input all the out of the variables in a one shot, and that this quantum attribution is going very well. So the very well discoveries, very well revolution can come in the drug discovery, because drug discovery requires this knowledge that at what angle, if we can have a carbon bond at 56-degree angle, and from having this 56-degree angle, if we are having a amoxicillin or we are having a paracetamol material, then if we having a 52-degree or 50-degree angle, can we have this material for the corona also? So that is a checkpoint. So can we have this geometry? Suppose we are having this geometry nowadays. So can we have this geometry also? And can this geometry have the parameter on that corona, that parameter on any other disease? So suppose dengue doesn't have the medicine. So maybe possible this symmetry is going and interacting with the DNA. So maybe possible it will form the solutions for the diseases. So that's why it is being said that this material design and this quantum chemistry and the drug discovery, all these are come under the same category. So here we can have a very much revolution by application of quantum computation. So yeah, of course, machine learning is of course we can have, but the main thing is that, and because of these factors, every country wants that they can have a computer. Every country wants they can have a quantum computer, not of a lower qubit, higher qubits. Because of the higher qubits, they can go on the discovering the medicine. And this time, whoever the country discovering the medicine first, we have seen in the 5 years ago, who can win the world's economy, right? So all the WHO is based on that. And because of this issue, all the countries are having the eye on the developing the quantum computation. And the basic thing is how to develop the hardware. Because software, we are having a very smart and high IQ level persons in the software field. So only the thing is we have to develop the quantum computation. With the same national quantum mission has been launched. So I hope in the 2 or 4 or 5 years or in the 10 years, we are able to develop the economical quantum computation. Okay, so now, yes. So these are the some paper outputs. So this I will upload on the PPTs. You can have these things. So so now we will have the some quiz kit session. Okay, for that, just give me a 1 minute, 1 or 2 minutes. I will share the this quiz kit platform. 1 minute, 1 minute. Launching the Jupyter Notebook. So yes. Mm. Mm. So yeah, yesterday we was doing the some Deuce algorithm. So somebody was demanding that what are the right consequences and what are the, yeah, I will upload that. I just remind this thing. I will upload all these things, the table of commands and table of descriptions, how they are working on the LMS portal. Okay. So now we are going to implement this Deuce algorithm along with this all the oracles. So there is a special demand from last session that how to construct the oracles also, because all the oracles I have left only with the wordings that this is the Oracle UF. But yeah, there is a personalized circuit for every Oracle. So Oracle for the Deuce is different. Oracle for the Shores is different. Oracle for the another algorithm will be a different one. Okay. So with this fact that we know that algorithm runs on the quantum computation facts. So let's see. Uh, so first we are importing all the environments, that quantum circuits, air simulator, and all that. So at here we are importing the quantum circuits and all the environments. Okay. So let the run, and then what we are doing that we are importing a empty box which is called a quantum circuit here. Okay, with this command. Okay, we are importing a backend air simulator. This simulator and this backend air simulator. We are importing a visualization command. We are importing a histogram. Okay. Now what we are doing, we are doing this. I think everybody will know this DEF is for performing any function. Okay. So if we are going to perform any function, then we have to give this command in the Python. It's a fact. Then this we are running this Oracle. Oracle is a name we are giving. Then we know that this underscore is used here as a word spacing. So the space is not used in the Python. So this we are giving the, we are constructing a function. What function we are constructing? Oracle. What function? Who will have the nature constant, and this constant value is 0. Okay. The name is will be a QC, right? So that we are performing here. And the one thing everybody I think know, but I want to emphasize that when the number line is there, when the number is there, then 99% of cases that yes, it is successfully done. Okay, so we don't have to wait. Yeah. So now we will go on to another command. We have constructed one function, because in the Deuce we are having four functions, right? The constant and balanced, right? So in the what happens in the cascade? Oh, sorry, in the Deuce we are having a two variety of functions. One is constant function. Another one is this is balanced balanced function, right? So balance function itself having a two things. Either the balanced means f0 having the 0, f1 having the 0 for even. Okay, now maybe f1 having a 0 or f0 having a 1. So there are function we will define like 1 and 2. 1 and 2. Constant is also having a two things. Constant means same value. Same value can be a 0 or can be a 1. So we have to define four functions: first, second, third, fourth. Okay. So same we are doing it here. We are defining the four functions. We are defining the four functions. The first function is the constant. Another function is constant 1. Okay. Now we are again writing this balance function. And remember, we are giving the command return to QC. So that means we are inputting the function in the QC and then giving the command to come out of that QC. Okay. Now one function is remaining. And see what the gate we are applying here. The gate we are applying it here, this Oracle constant. The gate we are applying X gate with the input 1. Gate we are applying C naught gate with the input 0, 1. Right? Gate we are applying on the first, we are applying 0, X gate, then we are applying C naught gate, then we are applying X gate. We know this can be achieved by these three gates. Yeah, almost written QC. So this we have forgotten here. We can have one thing written QC. Yeah. So now we will define the Deuce algorithm. So Deuce algorithm we will define by this function. Then we will define the in the same string, same cell, we will define what is QC now. After the QC, we will have some gates and Oracle functions. Yes. So there is error. So there is one column is remaining. Hmm. So we have defined all the four functions and the Oracle function. Inside we have decided another quantum circuit of this. This is a quantum bit, a qubit, and this is we are defining a classical bit. Actually, what happens in every circuit, we have to define a classical bit also for the register, work as a register. Register means it will work as a to store the qubits. It is only work as a store the qubit. Whenever required, we will call it from it here. Okay. So that's why now. Now we need to run this and run this all the Oracle one by one, all the functions one by one. Suppose we are putting this function constant in this. Then we want to check it the results. Oh, some semicolon is remaining. Yes. So at here, this Oracle we have run. We have run this Oracle constant function 0. So when there is a constant 0, we are running, we are expecting that this short. So here I recommend that always, because I have identified this my work is uh, to check whether the device is working. When I'm running this program, maybe in the medium projects, all of it is not required to come up with things, so they are not being studied by any mathematics. So what in R&D we have, since this is my personal student variability, that is there's one step only, hardly these two things are required. So just always on the, so it's checking that this function is working fine. And we have run the 1000 times, so 0 it's going. Now we can check another function. Suppose we can, instead of this 0, suppose we can put uh, here. Suppose we can put 1. Then let's see. See, there is no change in the function. Why? Because somewhere some of the persons are confusing about this point, that maybe it is going on to change because we have changed the constant 1. But no, because the function, the main algorithm we have designed in such a way that whatever be the value 0 and 1, it comes out to be a constant. So constant means comes out to be a 0 value. That is, we have run this function as a 1000 times, although it is giving a 0 values. That means our function is correct. Actually, very first time when I ran that before 4 years ago, then then I certainly surprised this one. Okay, so let's see another. Uh, there are 4 functions. Let's see another function. Suppose balance function. So what should come? So here I'm checking with the balance function. So see here. So here in the balance function, the output is 1. Now we can say that one function is remaining. We can also check it that one, whether it's coming things or not. See. Okay. So in this way, we can have all these things. So I will import, I will upload all these things. I will give to the Sushmita ma'am to upload all these things on the LMS. So from there you can pick up the things, the summary of commands, the summary of algorithms. In the Cascade, there I have here for the separate components in the Oracle. But in the Cascade, because all these algorithms are the a basic package. So in the latest version of this Anaconda prompt or something library, they have imported this as a whole package. So if you want, yeah, this Joseph, then you can import the same algorithm. There is no need to run the command separately. If you want Short's algorithm, then just import the Short algorithm. Here I have tried, but in my the we need to run in the Anaconda. So then I left it. Then I demonstrate on this only. But if you are having Anaconda, then you can import that directly the Shore's algorithm. Only the PIP import that once. Or in the Anaconda notebook, you can go on that and import that once. Just we are importing this quantum calculator here. Okay. So that's it from us, and I hope all of you have enjoyed these things and learned. So I will be happy if you have taken away some of the concepts, some of the things from here. If there are any further queries and doubts, then there is the last day, so I am open. Uh, so I'm waiting for your. You can ask and put the things in a chat box. Yes. Yeah, why we are using quantum circuits 2-1, why not 1-1? So this answer lies in how we have to design the oracle. So we are designing these oracles in the gate wise. So in the gate wise, that is the this inside the patterns, we are taking a 2-1. 2 represents for we have to take two quantum bits, and one representing we have to take a one classical bit. So one classical bit means as a register, we are only to store we are taking, but we need to apply a CNOT gate also. That's why that needs a 2 qubits. That's why we need a second qubit also. Okay, that's why we have taken this two. The first one is used to represent the quantum qubit. Second one is used to represent the classical qubit. Okay, so why not 1-1? I think it will be clear. Why always we count the zeros and ones in the output? Because this algorithm is like that. It gives only the whether function is balanced or not. So we have to count only zero and ones. So in the Hadamard gate, yesterday we are counting. Yes, we are counting zero and ones. So that zero and ones, because there are two possibilities in the Hadamard gate. There are two possibilities. Okay, so zero and one. So we need to check what are these two possibilities. If we are applying a suppose four qubit, three qubit, or multi qubit gates, then their basic states will be different. The basic state comprises like that 00, 01, 10, 11. In the three qubits 000, 001, 100. Then we need to check all that outputs, not only zero and ones. Okay. So there is one question from kindly wind up. Okay. So yeah, okay. So is there any query? Then it's okay. Otherwise, we are going to wind up all these things. So thanks for all. Okay. We'll hand over to the Sushmita ma'am.
Thank you so much. Thank you so much for all this 5 days of informative session. I hope this will helpful for our faculty. Thank you so much once again, sir. We'll definitely meet you again in next FTP or FTP, sir. Thank you so much.
Thanks.
Yeah, so dear faculty members, as you're all aware, today is the last day for this particular program. So I know you all have a query related to certificate. Certificates definitely will all receive it if you have marked your attendance, and if you secured above 60% of attendance, you will get the certificate. As we informed in the starting, the attendance is mandatory and it should be above 60%. Then only you will get the certificate. So the certificate will be issuing for your register mail ID. Okay. And the certificate, to issue the certificate, we require at least 10 days. So I request you all, please be waited for 10-15 days. Then we will issue the certificate for your registered mail ID if you are eligible. And as informed earliest, for the students, we won't issue the certificate. This is a faculty development program. So the students can attend for their knowledge, but the student won't receive the faculty development program certificates. And all the materials, recordings has been uploaded in LMS dashboard. If you want to go through the topics, yes, definitely you can go through. All the recordings is visible, like all the day 1 to day 5 recordings and also materials is uploaded. And if any queries or any questions to be asked, if any concern, you can drop a mail to edl@xlr.com. I'm just pinging the mail ID on chat, that is edl@xlr.com. Okay, I'll be there for 3 more minutes. If any questions or query, please drop it in a chat. I'll just answer for all this. Yeah, so some are asking for attendance link. I'm posting the attendance link once again on chat. You can mark your attendance. The attendance link will be active only till 5:30. Okay. Yeah. So I think there is no questions to be answered. Only you have to ask for the attendance link, which I have posted on the chat right now. So I assume that you don't have any query to be asked. So fine. We will wind up for the day. And thank you so much for joining for all the 5 days of faculty development program. We'll definitely be in touch for next upcoming FTPs or STPs. Thank you, everyone. Thank you so much for joining our program. Thank you.